Thank you so much for the introduction. Good afternoon, everyone. Today, I'm very excited to talk about eXpressSFU towards super-scalable video conferencing with SmartNICs. So this work is a collaboration between University of Colorado Boulder and Denver, Seoul National University, and Korea University. So as you know, video conferencing is one of the most popular internet applications in the modern era, with billions of revenue every year and very explosive growth rate. Current research also shows that employees spend almost 400 hours every year in meetings. And among the conferencing provider, Zoom is dominant, accounting for almost 50% of the market share. So with the popularity of video conferencing, I think it's very natural for the user to expect higher and higher video quality. And luckily, the current infrastructure is ready for high-quality video conferencing. So now we have very high-speed internet connection, more than 100 megabits per second. Secondly, endpoint devices are getting better and better. Now, most of the smartphones and laptops come with high-resolution camera and screen. And lastly, with the advancement of modern codec, 720p and 1080p video only require a few megabits per second. However, having the infrastructure is only half of the story. Supporting and scaling high-quality conferencing in practice from the provider standard is also very challenging. So one of the clear signs is that higher video quality often comes with high subscription cost. So for Zoom, lower quality, for example, 360p and 480p are available for free. However, 720p video conferencing requires a base subscription of $17 per month per user. However, and to enjoy 1080p video conferencing, they have to pay a whopping amount of $29 per month per user. Then you may be wondering why 1080p video conferencing is so much more expensive. To understand the reason, we measure the conferencing capacity at different resolution. So on the same hardware, and we found out that moving from 360p to 1080p, the serving capacity actually reduced by 6 times. And to understand where this burden comes from, let me first introduce the modern video conferencing architecture, which is the SFU, or Selective Forwarding Unit. So the SFU has 2 important roles. Firstly, relating the media traffic. So you can think of the SFU as a media bridge sitting between the participants. So the SFU will receive one uplink stream from each participant, replicate and distribute to others in the same conference room. And the second role of the SFU is adapting the media quality in real time. So in this case, I have one sender sending 1080p 24 FPS quality to the SFU. However, as you know, not every user can support this kind of quality. Maybe they don't have enough bandwidth, and they may have a small screen or weak CPU. So then the SFU have to adapt the media quality more appropriately for different endpoints to ensure the QoE. So next, you may be asking how exactly the SFU does this. Well, I got you covered. There are 2 ways to do it. The first way is using simulcast. So in simulcast, the SFU, each user will send multiple media streams to the SFU with different media quality. For example, 360p, 720p, and 1080p. The SFU will run the bitrate adaptation logic and select what quality should be forwarded to what user. And the second way to do it, a more advanced way, is using scalable video coding, or SVC. So in SVC, each user only sends one stream to the SFU, but this stream is encoded with multiple quality, SID and TID. SID stands for spatial index, controlling the resolution, TAD temporal index controlling the frame rate. And the SFU will send a combination of those quality layers to different receivers to adapt the quality. So as you can see, regardless of simulcast of SVC, essentially the SFU have to receive the media traffic, select, replicate, and forward to different receivers all in real time. And this creates a very tight latency budget for SFU processing. So to give you a concrete example, let's consider this case. So when I have one sender and two receivers with the SFU sitting in between using the 1080p 24 fps quality. The SFU first receive the frame from the sender, replicate this frame, and then forward to the two receivers. Because the frame rate 24 fps, which means that the interframe delay should be 1/24 or 41 milliseconds. And because one frame needs to be replicated into two outgoing frames, which means the frame budget is roughly 20 milliseconds. And each frame can be made of two packets, which means the packet budget should be roughly 10 milliseconds. So my point is that the SFU only have a few milliseconds of budget to actually process a packet and forward it to the receiver. So you may be asking, what would happen if the SFU is too slow? Well, because the video conferencing is a real-time application, late arriving frame at the receiver side are basically useless and will get dropped. So you can see that in our measurement, when I increase the number of concurrent users up to 125 and 150, actually I can observe 50% of the frame are violating the interframe delay and get dropped. So let us look deeper into the latency component of SFU processing. So as you can see, most of the latency overhead actually come from the data plane, roughly 80%, including the packet replication, packet encryption, packet decryption, and packet I/O. And this presents a very, very clear opportunity for acceleration. So due to our measurement, as you can see, the host CPU can perform the packet operation relatively well. However, the SmartNIC can perform much better. In particular, packet cloning is 4 times better. Packet decryption is 8 times better. Packet encryption is 3 times, and packet I/O can completely upload it into the NIC hardware. But to offload the data plane, there are a few design challenges. So as we discussed earlier, the SFU have to forward the media stream and also perform the bitrate adaptation all in real time. So it creates a tightly coupled control and data plane. So to tackle this problem, we have a few key insights. So the first insight is that the control plane only requires the packet header to perform the bitrate adaptation, and it also tolerates higher latency. The data plane, however, requires the entire packet, but it can be run in asynchronously with the control plane. For example, when a user experiences fluctuated network condition, the control plane can reconfigure a data plane to send a more appropriate video quality to ensure the QoE. So with this insight, we come up with a loosely coupled control and data plane solution. So with the key insight, we design a system with a few design considerations. So firstly, we want to leverage the existing SFU as much as we can because it's decade-long of engineering efforts. Secondly, we want control and data plane separation so we can offload the data plane to the SmartNIC for acceleration. And thirdly, we want to support both simulcast and SVC for broad endpoint compatibility. So let me run through our design overview. So I had three entities over here: the host, the SmartNIC, and the client. So for the control traffic, the host will handle this using the slow control plan, running the field function, for example, conference management and bitrate controlling. Using a set management API, the slow control plan will configure the fast control plan running on the SmartNIC, doing the media quality enforcement at the packet level. The fast control plan will send the packet decision to the data plan. This is the one that actually performs the packet operation we mentioned earlier: packet replication, encryption, decryption, and packet I/O. So the end result is that the media stream will reach the data plane on the SmartNIC, get processed, and forwarded directly from a data plane. So we can minimize the latency overhead. And asynchronously, the packet header will get extracted and sent to the slow control plane for bitrate adaptation. So given the loosely coupled control and data plane philosophy, we implemented a complete system. But due to the time limit, I will not go deeply into it. You can read more in our paper. But the packet flow looks like this. All right, so let me move on into our evaluation. So this is our evaluation setup. I have my SFU machine is a typical workstation, and I have roughly 100 client machines to generate the conferencing load. And then I have an Ansible server to automate our benchmarking and result collection. This is my client and SFU hardware application. Most importantly, we use a commodity SmartNIC, the Bluefield 2, which only costs a few $100 to ensure that our solution is very affordable to deploy. So firstly, about the latency improvement, we reduced the processing latency up to 8 times due to the efficient data plane uploading. This translates into the improvement in scalability, so we can support up to 400 concurrent users in large conference settings without the quality drop, which is 2 times better than the software-only solution, GC-Meet. For the media conferences of 50 users, we perform equally well, up to 2 times better than the software-only solution. For the small conferences of 15 users, we do even better with 3 times performance gain. And for the bitrate adaptation, even with loosely coupled control and data plane, our bitrate adaptation is still very effective and timely. So that you can see our system can adjust the bitrate according to the available bandwidth changes. And lastly, about the power consumption. So as mentioned in the keynote on Monday, power consumption is a huge concern in modern computing, and we are happy to say that our system reduced the power consumption for the computation up to 60% due to the efficient data plane offloading. And to summarize, we first re-architecture the SFU to decouple the control and data plane so that we can offload data plane for acceleration. Secondly, we support both simulcast and SVC to ensure the broad compatibility with endpoint devices. And we handle up to 3 times more concurrent users. And for efficiency, we got a computational power consumption up to 60%. With that, I'm happy to get any question. Thank you.